Welcome. Now we're going to talk about an equation for a plane in space. A plane in space is determined knowing a point on the plane and its tilt or orientation. Its tilt is defined by specifying a vector which is perpendicular to the plane. So as you can see here, I have a plane in space, plane M. We contain a vector from P0 to P, and N, this normal vector, that's going to be the vector perpendicular to it. So I'm going to use N, or its perpendicular vector, to help me define the tilt. So here I've brought in our definition for the equation of a plane. So suppose we have plane M and it passes through this point, P0, and that it is normal to this non-zero vector, normal is a fancy way of saying perpendicular, the non-zero vector N. And we're going to define N as having some AI component plus BJ component plus CK, where A, B, and C are constant values. A vector from P0 to any point P, which could be anywhere on this plane, creating a vector on the plane, is going to be orthogonal to N. Then M, this plane, is the set of all of the points, all of those points that exist as endpoints of this vector. So any vectors in this plane that are orthogonal to N. So if we know that they are orthogonal, then we know that N dotted with that vector P0 to P is going to equal that scalar 0. So when we dot product two vectors, we get a scalar. And you see that vector equation written right here. So we have a little bit more math. If we write this out like this, AI plus BJ plus CK dotted with X minus X naught I plus Y minus Y naught J plus Z minus Z naught K. We know that that dot product of those two vectors equals 0. And that leads us to this component equation with a little bit of simplification. I'm not going to prove that for us right now, and I'm sorry I drew over the picture. But that leads us, setting up that dot product, to this component equation. And so if I were to distribute that A and the B and the C to both of those terms and start rearranging, we find out that we can simplify this component equation to AX plus BY plus CZ equals some D value. And that D value would be, if I had this negative A naught, negative B naught, and this negative C, Z naught, if I pulled those over to the other side. So that's just a different way of writing it. They mean the same thing. Essentially, we just need to know this equation and that the dot product of those two would be equal to 0. In this example, we're going to find an equation for the plane which passes through the given point and is perpendicular to the normal vector. So recalling from above that normal equation, AX minus X naught plus BY minus Y naught plus C Z minus Z naught So we've got this equal to 0. I'm going to pull my A, B, and C. Those values are coming from N. And my X sub 0, Y sub 0, and Z sub 0 are coming from the point. So this is going to be 5x plus 3 plus 2 y minus 0. Of course, we don't need to write minus 0, so I've just got 2y. And that would be minus 1, z minus 7 equals 0. So at this point, we just need to simplify this. This is 5x plus 15 plus 2y minus z plus 7 equals 0. And rearranging our terms, we get 5x plus 2y minus z equals negative 22. So that is the plane which passes through the point and is perpendicular to that specified n vector. For our next example, we're going to find an equation through the plane. And the plane is defined as A, 0, 0, 1, B, 2, 0, 0, and C, 0, 3, 0. And if we think about the graph of this in R3, point A is up 1 unit on the z-axis. Point B is out 2 units on the x-axis, and point C is out 3 units on the y-axis. So our plane is this triangular slanted region. Now, if we want to find an equation through the plane, then the best thing for us to do would be to first find a cross product for AB and AC, because that cross product we know will be normal or perpendicular to the plane. So let's define what our two vectors are. AB is the vector 2, 0, negative 1, or rather 2i minus k. And AC is the vector 0, 3, negative 1, or rather 3j minus k. So these two vectors, AC and AB, they are forming this triangular plane. And we know that if we cross product these two vectors, I should have a vector symbol above AB, if we cross product them, we're going to find the vector that's normal to the plane. So AB cross AC, that would be finding the determinant of this matrix. We say I, J, K. I've got 2, 0, negative 1, and 0, 3, negative 1. So this is going to equal I times the determinant of 0, negative 1, 3, negative 1, minus J. It's always a minus for that second one. I've got 2, 0, negative 1, negative 1, and plus K, 2, 0, 0, 3. So simplifying this, I've got 3i plus 2j plus 6k. I'll leave that intermediate algebra out when we did the determinant there. So this represents our cross product, which is our vector, which is perpendicular to the plane. So at this point, we're going to take this n, and we're going to take a point. And we can use any of the 3 points. We just pick one, the simplest one, doesn't matter which. And then we're going to write our component equation for the plane. So I'm going to use the point A, which is 0, 0, 1. So I'll write that down here. We've got A, 0, 0, 1. So setting this up, my plane would be 3 coming from n, x minus 0 coming from my point, plus 2 from n, y minus 0 coming from my point A, and plus 6 from n, z minus 1 coming from the point, and that's equal to 0. So simplifying this, I've got 3x plus 2y plus 6z minus 6 equals 0. And the equation we get is 3x plus 2y plus 6z equals positive 6. So this is the equation of the plane passing through these 3 points. And again, we could have used any one of those 3 points here. So I hope that helps. Let me know if you have any questions.